Alright, time for another draftphysics.com video presentation. So I thought I'd talk a little bit about Newton's cradles because, frankly, the more you think about it, the more you have to ask the question, why aren't all these collision type experiments just done with this simple device? Because it really works really well. It's pretty efficient in terms of transferring energy from one object to another. And there's absolutely nothing. Okay, you can't. It doesn't even mention the idea on the Wikipedia page. So if I go to the Wikipedia page, I think I have it loaded. There's nothing on this whole page about using different masses. So they don't even suggest it. They don't even talk about it. Nothing. And so they claim it conserves both momentum and kinetic energy, but obviously it can't do that if you use uneven masses, as I've pointed out. So one of them has to die. And I would argue it's, obviously kinetic energy is the one that's not going to be realized as a fact. And so this is, so other than doing other research, I mean, there's these stack exchange threads, and they all get closed. So as soon as somebody kind of mentions the subject, they close the thread. So you really can't talk about, there's no real discussion. And the one thread where there is some discussion about a simulation, of different masses and what happens, they all concede that there's no experimental evidence available. So there's nowhere to check what really happens. So the simulation's just a mathematical model, doesn't have anything to do with actually what was observed and what was documented by doing experiments. So it's pretty funny that, again, it's just an example of how bad this physics is, that they can't, that nobody in their spare time with a Newton's cradle played around with these experiments to see what really takes place. And I think that's rather miraculous. So here's an example of one made out of pearls.
In here, how it.
Okay, and so he's gonna, move the big end and watch the little end fly off. Now, if the momentum is conserved, obviously the little end flying off is going to have more kinetic energy. So if the momentum numbers are conserved, there's going to be a lot less mass moving, and therefore, if you add up the motion of these smaller objects moving, it's going to end up with more kinetic energy if the momentum is conserved. It just has to happen that way.
Really pops out.
So you see that it does conserve this way, but the opposite way.
Now they get out of position a little bit, but it still shows that when you got mass times velocity, a certain velocity here, you end up with much higher velocity and a little further distance here. Now let's do the opposite.
Right, but it doesn't show anything because nothing's calculated, nothing's measured, so it's not worth much. Now, in this case, theoretically, by their physics model, the momentum should be increasing as you hit the small object into the larger object. So with each impact going to a larger object, we should be getting an increase in the momentum. And so this should be like, 4 or 5 times the momentum by the time it gets to the last ball. Obviously, that doesn't happen.
Let's take this one, this little one.
He really should have let it stop moving before he did it, too. So,
Do it like that. It has almost no.
Yeah, it has no effect. Yeah, exactly. So obviously, nothing got magnified, and you could really see that it bounced substantially back. So there's a huge reflection, which indicates by their theory that twice the energy went into the object, right? So whatever the reflection is, much more energy is supposed to be going into the object. So if it reflects 100 times, 100%, if you get 100% reflection from that little ball, that would mean twice the momentum went into the other ball, by their theory. Now, obviously, by a logical theory, it means nothing went into the other ball. That's why you got it all back, is because nothing went into the other ball. So I can argue this clearly. Illustrates, that it ain't what they say it is. at minimum. So there's a slow motion here, which is kind of
Fact.
nice.
We're going to try a little slow motion video of these
It's too bad he has his crap on top of it, but whatever.
transfer of momentum from one side to the other.
So I have shown the other video that has the 3 to 1, and you see it oscillate back and forth quite a bit. And obviously it doesn't make any sense to theorize that there's twice as much momentum. Now the other point about the momentum in Newton's cradle that I don't think is going to be denied by somebody. Now, again, I'd like physicist Michael to chime in, so maybe somebody can ask him, can somehow phrase the question, but like in a Newton's cradle with masses of a 3 to 1 ratio, is it true that when the small ball hits the heavy thing, it leaves with 150% of the momentum? Because if it does, that means when they both come back together again, there's 200%. And Newton's cradles don't give a care about direction, right? So there's no argument that when two balls come into and hit each other, that they do any calculation and say it's zero momentum. The opposite directions doesn't mean zero. So it's all just showing how they're just playing word games with all of these experiments, and trying to contrive this idea that somehow momentum and kinetic energy aren't completely opposing theories of reality. So, dramatic, in terms of, obviously, if the momentum is conserved in all of these littler balls, it has to be true, if you add up all their momentums, their masses and velocities. If its momentum's conserved, then the kinetic energy can't be. So, and you can see when they came back, they didn't do anything at all. They didn't force the other ball back. So whatever energy they had,
try our registered
it obviously didn't. It's too bad these commercials are in here. Can't get rid of it. Let's see. I guess I have to play it. Alright, I'll pause and get rid of this shit. Alright, so let's try this again. The slow motion. So watch
video of these transfer of momentum from one side to the other.
So when they're coming back, just notice that they all just bounce and nothing happens at the other end. So they bounce. They're supposed to be putting energy every time they bounce. They're supposed to be putting an equal amount of energy or more into the object they're bouncing off of, but there's no evidence they did that. I mean, the evidence indicates they just merely reflect. Okay, now watch the coming back part. So each one of these comes back and nothing happens here. I mean, barely any movement compared to what went in. Okay, it's a tiny fraction of the momentum was conserved, and most all of it was lost. So, it leaves me incapable of drawing much other conclusion than it's really wrong to think reflections are the byproduct of twice as much energy happening somewhere else. Because no, they're the byproduct of the energy being rejected and going back where it came from. Alright, so let's see what else I can find. I guess I just show this one again since it just came up in the Google search. So yeah, there's just not much to choose from on this subject. So I think it's kind of an embarrassment to science that there's so little documentation of a physics toy that really is an awful lot more than just a toy. I mean, come on. It's an excellent experimental tool. Alright, now their theory is that I just increased the momentum. Okay, this ball came in, hit a much bigger ball. I think the math says now it has 150 momentum. So say if this one went in with 100. So this one went in, hit with 100. It produced 150 going in the big ball, and there's 50 in the little one. I think that's their theory. Okay. It'll be something like that anyway. All right. And then when they come back together, I think everybody knows that they do conserve momentum. So when the 150 hits the 50, it's not going to go back to being 100. By their own understanding of the Newton's cradle, the 200 would have to be conserved. And it's not, clearly. So this one stops. It gives back all of its energy, all that it had. This one had 50, and now it's gained all the momentum of the other ball. So it seems clear that the only way that could work is there was never more than 100, clearly. And now it gets back what it had. It just now is a reflection. And only the small ball is moving, and so you just basically have 99% of what you put in comes back out, and there was no kinetic energy increase. There wasn't any momentum increase. Let's say, from their theory, kinetic energy would be conserved if momentum isn't. So if you can create free momentum, then you can conserve the kinetic energy, but you can only do it if you think Newton's cradles don't conserve momentum, which I think you have to say that would be impossible. So there's no example of a Newton's cradle where the momentum isn't conserved. So it just keeps doing the same thing. And I've already showed that, so clearly, it's kind of silly to think that this heavy ball has 150% of the energy that the small ball brought into the experiment. Seems pretty silly. Why is this stupid autoplay on? God, how many times do you have to turn that shit off? Irritating. I found a physics forum thread where some guy's talking about having two Newton's cradles, and I believe he combined a metal one with a marble one. Or he's making a comparison between the two cradles and the distance they move, but clearly they do have different masses. It's clearly pointed out the different masses. And the answer says, as long as the balls of the cradle have the same mass, which they do here, so of course they don't have the same mass, so the answer is totally pointless. And there's only the one answer, so just sucks. So this one's a little irritating. Chegg, or whatever the hell this is called. So they won't give you the answer, unless you sign up. You gotta do whatever this crap is. Yeah, such bullshit on the internet. But anyway, they're just asking the question, which is, one mass versus a two mass, and what is the outcome. So you get the question, but you don't get to see the answers. So that's kind of irritating. Well, found another example of somebody asking the question, but no answer available. So, not very useful. Alright, well, that's about all I could find. Frankly, there's just nothing on the subject. So, anyway, what I have done is, I ordered, because it was $2, those, I don't know what you call them when you're kids, these balls that bang together and they go up, down, and keep banging, clanking, and making horrible noises. And I thought they banned them, but apparently you can still buy them. And I figured, since they're plastic, I can drill one out, and put lead inside of it, and make a 3 times as heavy ball that's the same dimensions, and make a Newton's cradle of sorts, hopefully, out of that. So we'll see if that works. But again, it's not going to fix the fact that I don't have a camera really fast enough to capture a good enough quality image. But maybe I can do that. Well, I don't have a fast enough strobe either. Yeah, well, the Spar lab has that, whatever, the time gate. So he has one of those, so maybe he could put that upside down and do a Newton's cradle. But anyway, yeah, unfortunately, Toady, has, he purchased metal balls of different size, but he only did the one experiment, so. Uh, but again, this got to be filmed with a better than your iPhone kind of thing. But anyway, so it's an interesting subject, underdeveloped, underpaid, no attention paid by physicists really to the fact that this is really a test of the two theories, momentum and kinetic energy, and one of them is real and one of them is nonsense. And I think the Newton's cradle can prove which one is real. Because I think it does conserve momentum and it doesn't care about direction. All movement counts. It doesn't matter that they're going in opposite directions. It doesn't matter what direction it is. It all counts. So, and nothing disappears. They aren't made out of clay. They're not absorbing the energy. All they can do is exchange it. All right. So we'll say that's enough of a video, I guess. Short and on the one subject. Blah, blah, blah.